Okay, today we continue talking about exponents, in particular integer exponents today. Next class we'll do some stuff with radicals and then continue talking about radicals and exponents together in the following classes. Nothing really on the too near horizon, but our third quest is coming up on April 8th, a couple weeks out. Any questions on the calendar? Okay. So on the top of page 101, we'll start with our daily summary. Tyler? Good. Jeremy? Okay, so look at this first example here. 3 to the 0 equals 1. This was something that I just threw at you last class, right? So I said anything to the 0 is 1 with no explanation as to why that's true. The calculator confirmed it, but we really didn't have any reason to believe it other than Ian says. So here's the reason to believe it. Let's take a look at this pattern on the right-hand side here. Let's see, 3 to the first is 3, yes. 3 squared is 9. 3 cubed is 27, and 3 to the fourth is 81. All true statements. So let's think about how we might get from this number 81 to this number 27. And I want the same pattern to work going from 27 to 9 and going from 9 to 3. What's the pattern going down those numbers? Divide by 3. Agree? Take the number, divide by 3, gives you the next number. Fair? So then if I like this idea of, okay, the pattern is just divide by 3, then it sure feels to me like the pattern should continue to be divide by 3. So what do you get when you take 3 and divide it by 3? We get 1. And so looking now at the powers, there's 3 to the fourth, 3 to the third, 3 to the second, 3 to the first, 3 to the 0 is what we're trying to figure out what it means. What must it mean if this divide by 3 pattern holds? It must mean 1. Agree? It's really tempting to think 3 to the 0 is 0, or what does it even mean to take 0 copies of the number 3? But according to the pattern, we have to define it to be 1. And this pattern continues 3 to the negative 1, 3 to the negative 2, 3 to the negative 3, right? That's the pattern on the exponents. But if I want to just keep doing this divide by 3 business, then that gives me a way to define negative exponents. Ben? No, 3 to the 1/3 we will see in the coming class. We're going to talk about rational exponents here, 2 classes away. Yeah, 3 to the 1/3 doesn't have any meaning for us yet. Any number to the 0 is 1 except for 0. 0 to the 0 is not defined, but any other number to the 0 is 1. Okay. All right, so then looking at this one right here, we had the number 1, we divide it by 3 and we get 1/3. And doesn't that seem like a reasonable thing to define 3 to the negative 1 to be, just following the patterns? And we divide by another 3. This might be a little bit tougher for us to just do instantly, but 1/3 divided by 3 is 1/9. And so isn't that reasonable to define 3 to the negative 2 to be 1/9? And 3 to the negative 3, we're going to define to be 1 over 27. And then the last piece of this puzzle, 1/9 is really 1 over 3 to what power? Second, right? 9 is 3 squared. So then I'm feeling like I've got a new pattern here. If I see a 3 to the negative 2, it really means 1 over 3 to the positive 2. That's how we're going to define a negative exponent. So 3 to the negative 2 didn't have any meaning until just this moment. We say, oh, we got to define it to be 1 over 3 to the positive 2. That's the only way we can let this divide by 3 pattern hold. Page 101, Lucas. Okay, so we saw this formula last class, a to the 0 equals 1. Any number to the 0 is 1. We now have a reason to believe that. But now we've got a new pattern, new formulas that we should believe. If you see a number raised to a negative exponent, you do 1 over that number raised to the positive exponent. That's what we saw over there, 3 to the negative 2, 1 over 3 to the positive 2. Okay, this part here is not as obvious because we didn't have an example of it over there, but it turns out that if you have a negative exponent downstairs, You can bring that upstairs and make it positive. We'll see examples of all this. And then finally, if you have a fraction raised to a negative exponent, what does it look like we do to make the exponent positive? What do we do with this fraction here? We flip it. So if you see a fraction all raised to a negative, you can flip that fraction. X over y became y over x, and then make it a positive exponent. So let's try an example. We'll jump down to 3, and then we'll look at this kind of mnemonic way to remember things in 2. Okay, so let's go to 3 with Cody. Okay, so real common instructions that you're going to be seeing in the coming, you will see in the coming days is rewrite it so there are no negative exponents. We want to get rid of all those negative exponents, turn them positive according to the formulas on this page. The answers are here on the right-hand side. Cross them off. We want to just build them from scratch right now. Okay. Those are the correct answers, but we're just going to build them right now. So here's the idea. I'm going to start with a fraction line. That 10 right there, is that 10 affected by the negative 9 power? Remember that exponents are very, very weak. They don't have much reach. So that 10 is just hanging out there unaffected by the r to the negative 9. So the 10 is just staying where it is. It's on top. It's still on top. The next thing I see is r to the negative 9. In order to make that r to the positive 9, I need to take it and move it. That r to the negative 9 is currently upstairs. We're going to make it like a 1 over and put it downstairs. So that goes downstairs and becomes r to the 9, positive 9. This is the key for today. And if you see a negative exponent, you move it to the other place. It was on top, we move it to the bottom and make it positive. The next thing I see continuing on top, I'll just put little check marks here. We've dealt with those two factors, the 10 and the r to the negative 9. The next one I want is the d to the negative 7. It has a negative exponent, so we move it. Where do we move it? To the bottom, and we make it d to the positive 7. Everybody see that? Negative exponent tells you to move it to the other spot. If it's on top, you move it to the bottom. If it's on the bottom, we'll see right now we're going to move it to the top. Okay, so we're finished upstairs. Now we're ready to deal with the downstairs. That 25, does that 25 have a negative exponent? No, it's unaffected by the negative 5th exponent. So do we move the 25? No, there's no reason to move. It's really tempting to move it, but it doesn't go anywhere. It's just plain old 25 on the bottom and it stays there. So that one's done. Next one we have is r to the negative 5. It has a negative exponent, so we move it. Where do we move that one? Upstairs. It was downstairs, we move it upstairs. So that's going to go upstairs and become r to the 5th, positive 5th. Again, the idea is a negative exponent tells you to move it to the other place. If it's up, put it down. If it's down, put it up. Make the exponent positive. That last example where we had r to the negative 5th on the bottom was an example of this one. R to the negative 5th on the bottom becomes plain r to the 5th up on top. That's that pattern. Okay, and the last thing is d cubed. Move or stay? It stays because it's not negative. It's just d cubed. It has no reason to move, so it stays down there as a d cubed. So we dealt with all 6 of those factors. What can you say about all the exponents now? They're all positive. Great. We have accomplished what we were after, to get rid of all those negative exponents. The last thing, though, is we always have to simplify our final answers. So we're going to simplify this thing. First, 10 and 25 have a common factor of 5. So what does this become when you pull out and cross off that factor of 5? 2 and 5. Everyone agree? What do I do with the power on the r's here? R to the 5th and r to the 9th. I subtract them. We know that from last class, division becomes subtraction in the powers. So you could do 5 minus 9. How much is 5 minus 9? -4. But if you do that, all of a sudden you got another negative exponent. We worked so hard to get rid of negative exponents. So how about we subtract in the other order? 9 minus 5. That gives me +4. But where are those r's when it's a +4? They're on the bottom. If you just think about listing out all the r's, list out 5 r's on top and 9 r's all right next to each other on the bottom, and you cancel some, where will they be left over? On the bottom, because that's where there's more. So r to the 4th down there. And then for the d's, what do I do with the 7 and the 3? We're going to add those guys up, and we get d to the 10. So that's our answer right there. Positive exponents completely simplified. Questions on that one? Okay. So the last thing I want to demo today, and then you'll do the group thing, is on the next page. And it's all about something called scientific notation, which is related to exponents, which is why it's here in this section. Lucas, number 4.
Scientific notation allows us to easily work with very large numbers with very small numbers. Right numbers is format by writing.
Okay, so that's going to be our definition. It'll make sense once we look at these two examples. So we want a number between 1 and 10 multiplied by a power of 10. Irene, part A. Good. Mm-hmm. Okay, so that number is pretty hard to read, and Irene did an excellent job of recognizing pretty quick that that was 15,460 billion, but that's a lot of zeros to have to count out, right? It's kind of annoying to deal with that number the way it's written. So we'll use scientific notation. Scientific notation says you got to have a number between 1 and 10. So what you're going to do is you're going to take the decimal point, which currently lives here. We don't need to write it in this form, but we know it's there. And you have to move that decimal point any place you want in this number, but you have to build something that's between 1 and 10. So for example, I could put it right here. Don't put it there because that's not where it belongs. But that number is now 15.46, yes? And a bunch of zeros that you don't need to say anymore. But 15.46 is not between 1 and 10. It's too big. So where should I put this decimal point? Between the 1 and the 5. Because that number is 1.546, which is between 1 and 10. So 1.546, and then a bunch of zeros that you don't need to write because they're after the decimal point at the end. And then it says multiplied by a power of 10 times 10 to the something. Okay, so how many spaces are there between where the decimal point was and where we moved it? 3, 6, 9, 12, 13. Is that all right? So then up here, I'm going to put a 13. And that's it. 1.546 times 10 to the 13 is the same as 15,460 billion. Because we know that multiplying by powers of 10 is really easy, right? Multiplying by 10 to the 13 just says, take that decimal point and move it 13 places to the right, which is exactly what the answer is supposed to be. Okay, so that's great. So that's how we deal with a really big number. Let's go to Marcy for B. Good. Again, really annoying to read that number. It's difficult to understand what that number is, but in scientific notation, hopefully it'll be easier to at least look at. Okay, the decimal point is currently right there. We need to make a number that's between 1 and 10. Where do you have to move that decimal point to make a number between 1 and 10? It's just right after the 2. It's the only choice that we have. So we have to put the decimal point way over there. So I'm going to write 2.0, like there's an invisible 0. You don't need it, but I'll just put it there so you can see. Times 10 to the, okay, and we ask the same question as before. How many places from where the decimal point currently is to where we want to move it? So how many spots is it moving? Just 7? Yes? Is it 7 or 8? 3, 6, and then one more. So I think it's 7. But if we left that as our answer, we'd be wrong, because we know that multiplying by 10 to the 7 makes the number really big, yes? At that point, 0.0000002 is a really small number, very close to 0. So Savannah had it right. What did you say, Savannah? Yeah, -7. Because we know from, again, some previous math class, multiplying by 10 to the -7 says take that decimal point and send it 7 places left. And it gives you a number very close to 0, which is what we're after. So I'm not a fan of just memorizing, like multiplying by 10 to the positive moves the decimal to the right, and multiplying by 10 to the negative moves the decimal to the left. What I am a fan of understanding is that 10 to something big is 10 to the 13 is a big number, and 10 to the -7 is really tiny, really close to 0. And that's all that I need to guide me to whether it's a positive or negative. Right and left is too easy to make a mistake, I think. Questions on that? Okay, so there are 3 separate activities, so you guys are going to have to hustle to get through them all. I know you can do it. Raise the flag if I can help.